Hello, my YouTube fans. Let me just get around here. Well, I actually had started this recording, and for some reason my computer just decided to restart in the middle of my recording. So I have to do this all over again. Anyway, as you can see, I'm going to be doing a video on telescopes. This is my own personal telescope. This is the only one I own. It is the Orion's 90mm EQ AstroView. I got it back in 2011 or 12, I think it was. Haven't taken it out in a long time. Even though we had that conjunction of Saturn and Jupiter, I was not able to see it. I can still see other things, but I'm getting kind of old to be carrying this thing outside in the middle of the night. But in any case, it was Matthew Beal who asked me if I could do a video on something on astronomy or telescopes. He asked me if I can do on chess books or astronomy and telescopes. So this is a video on telescopes. So what are you looking for, and how do you understand the numbers and everything they give you about telescopes? So first of all, if like everything else during this pandemic, things, all these little hobbies and whatnots are becoming more and more popular, including chess. The other thing, of course, is astronomy, amateur astronomy. So some people out there are starting to buy telescopes, and especially with the conjunction of Jupiter and Saturn, people were looking to buy telescopes. Now, I know this video is a little bit late for that, but if it's a very interesting hobby. Albeit a bit expensive, especially if you start going into astrophotography, because photography itself is completely too expensive for me. I never even done it. But so let's try to understand what a telescope is and what it does. When you buy a telescope, you're gonna see specific specifications like focal length, magnification, and things like that. First of all, you don't buy a telescope by magnification. You buy a telescope by its quality of optics and things like that. So what is magnification? Magnification is simply how large the image looks to you in comparison to what it looks like, with the naked eye. So, all right, so how do you figure out magnification? Well, this is a 910mm focal length telescope. And that literally means 910mm, by the way, is something like 35.8 inches. So we're looking at a yardstick, looking at 36 inches, right? So if I was to put this is, by the way, the actual, let me just take this cover off, because the actual objective lens is actually over here. So this is a light shield. So, the actual objective lens is somewhere around the middle of this, right? So I can literally take this yardstick, and you can see that it goes to the bottom where the focus is. Now, of course, it's not actually in focus right now. I would have to pull that out. And then you have the star diagonal, which is a prism, to point the image upward. So you add that distance. If I didn't have that in there, I would have to take this thing all the way out here to get it to focus. But as you can see, you can reach almost the full yard. So that's 910mm focal length. So focal length literally is the distance, and I know I'm not looking at the camera, but I'm looking at the telescope. So the distance that the focal point comes to from the objective lens. So the light comes into here, a star or planet or whatever you're looking at. The light comes in here, and it focuses down the tube, and it gets to a focal point 910mm later. So that's literally what the focal length is. Then you have the 90mm part. The 90mm is the diameter of the objective lens. So this is the lens cap. Okay, I'll just take this off. This is the lens cap and the light shield. So this is literally 90mm, which is what is it, like 4 inches, something like that. Okay, so the diameter of the objective lens. And here's the objective lens. Let me see if I can loosen this up a bit so I can tilt it down for you. Don't know if I'm going to be able to not hit the wall. Oops, hit the wall. Don't want to do that. Okay, so I'm just going to... Okay, that's close enough. There you go. So that's the actual objective lens. And it is literally 90 millimeters in diameter. Okay? So let's go ahead and put this back on. So when you're buying a telescope, the one thing you don't do is you don't look at how much power. You don't buy a telescope by magnification. Magnification comes with the eyepieces. Okay? And the way you calculate magnification is you divide the focal length by the focal length of the eyepiece. And the eyepieces are marked 10 millimeter, 12 millimeter. So I'll show you some eyepieces. So I had this little box that I took from a game or took from something. I don't remember what I got it from, but I got those metal boxes, and I made my own lens case for it. So you got these eyepieces that come with the telescope are marked. This is a 25 millimeter. I don't know if I can see. I'm looking at the TV right now to see if I can see that, because my TV is way over there. I don't know if you can see that. I don't know if that's in focus, but anyway. Yeah, it's 25 millimeter, for example. I believe that's 35 power, 35 times. If you divide the 25 millimeter into 910 millimeters, you'll come up with the right amount. In fact, I could ask Alexa, but I have the microphone off right now. So this is, let me see what this one is. It should be a 10 millimeter. This is 12.5 millimeter, actually. Okay, this is around 75 power, 75 times, something like that. Okay, and then you have the 10 millimeter. Okay, and that's an easy calculation. 910 millimeters divided by 10 millimeters is 91 power, 91 times. So that's like pretty close to 100, right? Then I have the special lens. I'm going to get into these lenses a little bit more later. Okay, this is actually an expensive lens by itself. I'm going to show you that. I'm going to show you more detail on them later. So we don't buy telescopes by power. We buy telescopes by the quality of the optics and you know, what suits you, what you can, are you going to be able to carry this thing outside? Are you going to be using it just at your house in the backyard, etc. I like the refractor. There's two types, basically, two types of telescopes: refractor, reflector. There is a third type called the catadioptic, which is actually a correction lens over the top of the reflecting telescope. But the basic two types are refracting and reflecting telescopes. The reflecting, of course, uses a large mirror as a primary, objective, and refracting, like this one, uses a lens. Now, the optics on the lens, when it comes to refracting telescopes, it's never just one kind of glass. It's always at least two types of glass sandwiched together, and that's because every kind of glass has its own refractive index. And what you get is your basic cheap magnifying glass that you get from the dime store. If you try to use that, for example, you're going to see color distortions. So they use two different kinds of glass with two different refractive indexes and tries to bring the colors together. It's not perfect. There's actually what they call apochromatic, which uses a triple layer of glass and three different kinds of glass. And they're generally short focus lens telescopes, and it's hard to get any high magnification out of them because they're generally shorter focus. But in any case, getting back to the basics. So I have the star diagonal in here. This is the prism, which I'm going to pull it out to show it to you. And the eyepiece goes in here. Okay, so this is the star diagonal. Okay, and the eyepiece goes here. Let's put that in there. So there's two types of mounts that you can get. There's the Equatorial Mount and the Azimuth Mount. I'll be honest with you, I got this telescope because it was on sale. And it's got an Equatorial Mount. But quite frankly, I've never really used the Equatorial Mount to its full potential. An Equatorial Mount literally means, okay, do you see this angle here? Literally, the telescope is pointing at a 40-degree angle because the latitude here is 40 degrees. So you set the Equatorial Mount up, and this is adjustable. Depending on where you live, you can adjust the tilt, and I have it set for 40 degrees latitude. So theoretically, I should be able to take this telescope outside, point it directly at the North Star, and set it up perfectly, and then I'll be able to supposedly follow the star or follow the whatever, then I point it at some other object in the sky that I'm looking at, and I should be able to follow it simply by moving the right ascension. The right ascension is the clock. As you can see, let me just tighten this up so it doesn't move. As you can see, it looks like the telescope is going in a curve because it literally will follow the rising and setting of a star or a planet, whatever it is that you're looking at. Okay? When it's not set up exactly, when it's not calibrated exactly, you're going to have to continue to adjust it. There's two adjustments on this. There's the declination and right ascension and here. If you set it up right, you should be able to follow the star, the planet, or whatever it is that you're looking at. Say you're looking at the moon, for example. You should be able to just simply adjust this one knob to follow it rising and setting. But you have to set it up just right. You have to get it calibrated just right. And I never really got it right. I've done some solar projection videos, and that's hard to set up because you got to point the thing at north, and there's being it's daytime, you're doing solar astronomy. Being it's daytime, you can't see where the North Star is, so I had to use a compass. And of course, compasses are off. The magnetic north is completely off compared to what the actual true north is. But I got it pretty close one time, and I was able to use the one knob for a little while, and then once in a while I'd have to turn the other knob, that sort of thing. But in any case, let's get back to the basics here. So when you're buying a telescope, you're buying a decent optical instrument, and the mount, of course, you can't see the whole tripod here. I have it somewhat extended. The mount is heavy. Okay, so it's stable. This is a counterbalance. When you're setting up the telescope, what you're going to do is you're going to slide the telescope in and out of this bracket, this way or that way, and it should be balanced. See, actually, it's not balanced. You see, with the eyepiece in it and it's almost in focus, it's not quite balanced. So I would loosen this up a bit, and I would slide it forward if I can. Okay, so now it's more balanced. You see? Somewhat. Okay, and tighten them back up again. And when you're setting up the telescope, that's what you basically do. I could mark it. I could, basically it's 5 fingers from the letter N in Orion, or a little bit more than 4 fingers if I use that. I could do it something like that. It doesn't have to always be exact, but it helps to be stable when you're out there and you're trying to look for things and it's hard to adjust the telescope. It helps it to be stable and not falling all over the place. Okay. So, also, by the way, this viewfinder is a telescope by itself. This is actually a 7-power telescope all by itself, and it actually is removable. And it's very helpful to have a removable viewfinder when you're doing solar astronomy, because you don't really want a second telescope on this thing. For one thing, you never, ever, 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 ever look through the telescope pointing it at the sun unless you have a solar filter on the objective side of the telescope. That's filtering the sun before it gets into the telescope. So you don't want this extra telescope on there, but to start to burn ants on the ground and stuff like that. But that's how that goes on. It goes on like this, and tighten up that little screw there. So when you're buying a telescope, you want to say to yourself, well, you know, I don't want nothing expensive. Then you know, you buy yourself a beginner's telescope. You can spend as little as $100. You know, again, don't buy the dime store $20 piece of junk that they got that's worthless. It's not even, you know, you're not going to be able to see anything with it. It's going to be all jittery. I'm not saying you have to spend $1,000 on a telescope, but if you're going to do it, you know, they have some really nice tabletop telescopes and stuff. They're little ball type of reflectors and stuff like that. They're actually really cool for a picnic and stuff like that. You know, nighttime falls, and you can sit at the picnic table and put this thing on the table and look through, you know, for a few planets and stuff. These are basic reflecting telescopes. But this is actually capable of attaching a clock drive on it. And again, you can only put a clock drive on an Equatorial Mount. I can literally, you know, as long as I set it up perfectly, again, the clock will adjust only the right ascension. In other words, it'll only adjust, you see, okay, and it'll follow the planet, the star, or the moon, or whatever it is that you're looking at. So, all right, so let's I'll give you a little lesson about how to figure out different things. Magnification is the focal length, which on this telescope is 910 millimeters, which is actually 35.8 inches. And you can see it's almost a full yard. You can see that's the actual focal length. That means the focal length literally means from where the lens is, and of course I don't know if I showed you this already because the lens is actually here. So it's like, okay, so it's somewhere in the middle here. So from there to where it comes at the focus is literally 910 millimeters away. And the way you figure that out, I don't remember if I showed you this yet because I was actually starting this recording, and when I turned around, the computer decided to restart. So I had to do this whole video all over again. But in any case, you take any eyepiece. For example, it comes with a 10 millimeter eyepiece. Okay, 10 millimeters literally means that the focal length of this eyepiece is 10 millimeters. So you divide the focal length of the objective lens by the focal length of the eyepiece, which is written on the eyepiece, and there's your magnification. So this gives me 91 power, 91 times magnification. It's 10 millimeters. These are Plossl eyepieces. These actually are standard now. When I had the Celestron telescope that I had years ago, decades ago, they came with orthoscopic eyepieces. They were different. They were cheaper eyepieces. This is a 10 millimeter eyepiece. You can see the hole to look through is kind of small. Some people use Barlow lenses, which are lenses that you add to the eyepiece before the eyepiece to double or triple the magnification of that eyepiece. I don't like to use them. Let me get closer to the microphone. I don't like to use them. I think it's sometimes just adding more lenses in the way. I like to use the actual eyepiece, and if I want a higher magnification, which I do have one, I buy one expensive lens or semi-expensive lens. Of course, I never could afford the Naglers. The Naglers are several $100s a piece. They're crazy. If when I wanted to get this telescope up to its maximum magnification, which I'm going to talk about in a minute, I bought myself one eyepiece extra, and I'm going to show you that now. I bought a 6 millimeter eyepiece, which brings this telescope up to about 150 times, maybe 154 times. I'm going to calculate it. Actually, you know what I'm going to do? I'm going to turn my Alexa's microphone on. Okay, and I'm going to ask her what the actual calculation is. Are you ready? Alexa, what is 910 divided by 6?
910 divided by 6 is approximately 151.6667.
So 151 power, 152, whatever.
100 to the power of 51 equals 1 tetragrammaton.
Alexa, stop. Okay, that's why I turn the microphone off, because I'm talking and she'll interrupt. So this is a 6mm eyepiece, but this is a special eyepiece. I forgot what they call this. This eyepiece was on sale for like half price, and it cost me $60. The beauty about this eyepiece, and I showed you the 10mm, and I showed you how small that hole was. This is even a higher power, but check a look at this. It's like looking through a porthole. That's where you put your eye. Okay, so I was able to get this telescope up to 151 times just by buying the right eyepiece, without having to buy any additional Barlow lenses and things like that. Of course, this goes in here, and that's what the telescope will look like with that eyepiece in there. I don't want to put that in there right now, but I'm going to sort of just show you. Okay. All right. Let's talk about magnification. You don't buy a telescope by magnification. You buy it by quality of the optics. There is a limit to what a telescope can magnify to, because it's almost like your TV or your computer. If you blow up a picture to the point where it gets all kind of blurry or pixelated, it's the same sort of thing with telescopes. It also gets darker in a telescope. The higher you magnify it, the darker it gets. But I got to tell you, this is a fairly bright telescope. It's brighter than my Celestron I used to own, and we'll talk about that in a second too. There's a thing called Dawes limit. Now they used to say it's like sort of an arbitrary number. They used to say it's 2.4 or 2.2, I forget the exact number, times the diameter of the objective lens is your supposed maximum magnification for that telescope. There's a couple of reasons for that. One being what I just explained to you about the you can't focus after the limitation. You can't get a clear focus on it. It's kind of blurry. It's kind of pixelated, so to speak. The other thing, of course, is darkness. The third thing is, the higher magnification you go, the faster something will move just by the Earth spinning. Something will pass the field of view. Okay, so you don't really want to get that high magnification unless you have a large enough telescope. If you're really looking to do deep sky, if you're looking for galaxies and nebulas and things like that, this is not the best to do that with. I have seen the Ring Nebula with this. I have seen a few brighter nebulas, but if you're really interested in looking into deep space, you want to get yourself a large mirror reflector telescope. They come, 8, 10, 12 inches in diameter. That's why they call them light buckets, because they gather a lot of light. And those, of course, the larger the diameter, the more you can magnify. So, you get yourself a good 10 inch, and you're talking about 10 inches is how many? Alexa, how many millimeters is 10 inches?
10 inches is 254 millimeters.
There you go. So 2 times 254 is literally, 300.
2 times 254 is 508.
Thank you, Alexa. Stop now.
Anytime, Patrick.
See, this is why I turned the microphone off earlier. So you can literally magnify something, more than 400 times and still have a clear view. And on top of that, it gathers more light. And you can see deeper into space. So the bigger the diameter, the deeper into space you can see. A refracting telescope like this one here, 90 millimeters, is excellent for planetary. In fact, Jupiter was too bright. I had to use. I don't even have any. These eyepieces come with threads where you can. They have filters that you can screw into them. Okay. I really can't see the threads, but there's threads in here that you can screw filters into. And I didn't buy any of the filters. So when I looked at Jupiter first time with this telescope, it turns out that this telescope is so bright that Jupiter was literally too bright. And I just happened to have an old half of a polarized filter from a camera with that I had one time, and I was holding that in front of it to take the glare out. As you can see, it takes the glare out. See, so that's what I was using, just holding it in front of my eye like this here in front of the telescope. But I have a couple of other flashlight filters that I was also using, you know. But I have to, one of these days, I'll buy some actual filters to screw into the eyepiece. But in any case, and again, it depends on what you're looking for. It depends on what you just want to do. Are you going to go out and start searching for the dimmer nebulas and galaxies and stuff like that, which is something I'd like to do? Or you're really just going to take it out for an hour or two and look at the different planets, look at the rings of Saturn and things like that. This is excellent for that. I have seen the Ring Nebula with this. It's kind of faint in this telescope, but I have seen it. These skies here are a little bit light polluted, but I have seen it. You know, certain double stars you can see. Not the really close ones, but for example, Albireo, which is the one of the stars in the Cygnus the Swan, or otherwise known as the Northern Cross, is a distinct blue and a distinct yellow star right near each other. This is beautiful for that. Things like that. So let me see. I don't remember what I explained because like I said, I did this video twice now, so I'm trying to remember what I left off when I got cut off on my computer. But so to reiterate, this is an equatorial mount. You would point this at the North Star, and then you should, if you do it exactly right, you should be able to just use the one knob on the side here just to adjust the right ascension, and it moves the telescope like this. You see how it looks like it's literally oops, I got the wrong one. It looks like it's literally curving, as you can see. Okay. But generally speaking, the first telescope I had was the Celestron First Scope 80, which was an 80 millimeter. I didn't talk about F ratio. I'll tell you that in a second. And it was an azimuth mount, which means altitude, azimuth, which, you know, up and down, left and right. And really, because I never really got this thing adjusted properly anyway, really that's all I should have had to begin with. But this telescope, again, was on sale, and it was 90 millimeters. It was a little bit brighter. Actually, it's a lot brighter. Let's talk about F ratio. If anybody's into photography, they know about f-stop and F ratio. Just like cameras, telescopes have F ratios. The F ratio on this telescope is about 10. It's actually more like 10.1, but the manual literally says 10. So to get the F ratio, you divide 910 millimeter focal length divided by the diameter of the objective lens, and that's where you get your F ratio. So my Celestron had the same focal length, but it was only 80 millimeter in diameter, so it was an f11.4. This one's a 10.2, so one f-stop difference, maybe slightly better than one f-stop difference, and it's a lot brighter. Again, if you know about cameras, they got the iris that closes, opens, and closes when you adjust the f-stop on the lens. It literally is closing off the aperture. It is dimming the light, and that's why it helps. Certain artistic photography deals with taking longer exposures with the f-stop down, and it clarifies or does whatever effects you've talked about. But it also darkens the picture, so that's why this one's so much brighter. So, okay, we talked about the Dawes limit, we talked about the F ratio, focal length. By the way, did I mention, I don't know if I did this on the first video or if I did this a second time on here, but this is actually a telescope in itself. This is actually a 6-power This viewfinder is a 6-power telescope all by itself. And it is removable. And when you're looking at the sun, like I was doing in my videos from a few years ago, projecting the sun, you want to remove that. So if you buy a telescope without a removable viewfinder, I would suggest keeping the cap on the front. Also, some of them aren't even telescopes. Some of them are just like holes with crosshairs in them. But never, ever, 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 ever look at the sun with a telescope, unless it's specifically designed with a solar filter on the front, or you purchase a solar filter that goes on the objective lens. That is, you filter the sun out before it goes into the telescope. Okay, you will go blind. I can light my cigarette off of the end of the telescope if I wanted to damage my eyepiece. So they do have telescopes that are built in. They're called solar view telescopes that they have built, objective lens solar filtered for the purpose of actually studying the sun. My videos are about projecting the sun, so I don't have a solar filter on here, but I was projecting it. You can literally use the telescope as a projector to project the sun on a screen. So go back a few years and look at my YouTube channel, search back for solar projecting, and you may find my videos. So I don't know. What else do you want to know about telescopes? I know I don't have. I'm not actually on air, so I can't actually ask you that question and expect an answer, or expect a question. But let me see if I left anything out. I don't know. So when you buy eyepieces, you're buying it by the quality of the eyepiece. You're buying it for the magnification, and if you're looking to just buy one lens to expand the two lenses that comes with it, you can buy a Barlow lens. A Barlow lens, either they come in 2.5, or 3 times the magnification. And what they do is, for example, I have the 26 millimeter eyepiece, which is approximately 75 times. Alexa, what's 910 divided by 26?
910 divided by 26 is 35.
35, right. Is it 26 or is it... Oh, it's 25. Alexa, what's 910 divided by 25?
910 divided by 25 is 36.4.
Okay, so 36, 35, 36 times. So you put a Barlow lens in there, say a 2 times Barlow, and you have 70 times. Right? Put a 3 times Barlow, and you have your 150 times. So, I'm sorry, 35, 36. You have like 90, 100 times. Things like that. So you put the 10 millimeter eyepiece in there, instead of 100 times, you have 200, which is ridiculous. Because the telescope, maximum magnification. I don't know if I covered that. The maximum magnification on this telescope, using Dawes limit, is approximately 180 times. Maybe I can push it to 200 because it is very bright. But generally speaking, my best eyepiece, I think I just showed you that. Wait. See, again, my computer had shut down all by itself while I was making the first video. So let me make sure I actually showed you that. So I don't buy Barlow lenses. I like to buy the eyepieces specifically by millimeter in order to get the magnification I want. And just in case because of the confusion of how the computer shut itself down, this is the 100 power eyepiece. No, this is 12.5 millimeter. This is the second eyepiece I bought. This is about 75 times. You see the hole in that? That's where you put your eye. It's not too bad. It's not that small. I've seen worse. But it's hard to look through these smaller holes. And the 10 millimeter eyepiece is just a little bit smaller than that. And these are Plossos. These are good eyepieces. They come with the telescope. They can't, the 10 millimeter and the 26 millimeter came with the telescope. So this was the high power and that one was the lower power. And the 26 millimeter is low power and it's good for looking at diffuse nebula or whatever, or even full moon or something like that. But the full moon, of course, you got to use a filter. Here's the low power eyepiece, and you can see it's a very big hole to look through, and that's where you put your eye, and that's really nice. But this is a low power eyepiece. So as you go up in the higher power with the same type of eyepiece, you look, let me talk closer to the microphone. The higher power of the eyepiece, the smaller the hole is to look through. So the 10 millimeter was about as small as I wanted to get for my eyes. But I wanted a higher power. I wanted to bring the telescope up to above 100 times. I wanted to bring it close to the, and I know I'm looking at the microphone right now, and I know you're seeing the side of my head. I'm sorry about that. I'm trying to talk into the microphone. So I wanted an eyepiece that was higher power than a 10 millimeter without buying a Barlow lens. And look at this. This is a 6 millimeter eyepiece. And again, I don't know if I showed you this already because I had the computer problem before, so I might be repeating myself, and I apologize for that. But look at that. It's almost as big as the low power eyepiece. Not quite, but this is 154 times. And look at that porthole. Looking through this eyepiece when I was using it for looking at Saturn's rings and stuff. It's like looking into a porthole into space. So this eyepiece actually cost, it was like half price. It was like $60 by itself. Of course, I can't afford all this stuff anymore. This was way back in 2011 when I bought this stuff, so that's when I had a life, in any case. But so there you have it. That's a refracting telescope. If you want something that you're going to look into deep space, you want to get yourself one of those light buckets, large diameter telescope. Of course, the cumbersome idea of being able to carry this thing and depending on where you're going to go with it, if you're just going to do it in your own backyard, it's not so bad because it's right out the back door, that kind of thing. But if you're just looking, for example, to look at the planets, especially since we had that conjunction recently, of course now they're starting to set a little early now. These telescopes, these refracting telescopes, are perfect for planets. In fact, like I said, Jupiter was actually too bright. So there you have it. I hope you enjoyed my video and me looking at the side of my face, and I'm going to look into the camera now and talk to you straight on. I know here I'm going to pick up the microphone now that my hands are free. I hope you enjoyed this video, and thank you for watching, and I hope I helped you understand something about telescopes. If there's any questions, please leave a comment. Oh, one more thing. Anybody who owns a telescope should also have a handy pair of binoculars with them too. I have a pair of actually I have two pairs of Bushnells, 7x35, so one is better than the other. I'll quickly show you that. So what does 7x35 mean? 7x35 means 7 power, 35 millimeter objective lens. That's what that means. And I'll show them to you. There you go. These are my better Bushnells. I have an older pair that I got from somebody, but these are my see, that's actually 35 millimeters in diameter. So that's 7 power, 35 millimeter diameter. Okay. Your standard hello there Bushnell binoculars. They're good for looking at wide fields of different star clusters and stuff like that. You'd be surprised how many more stars come into view when you look through a pair of binoculars. They're also excellent for looking at the moon. I mean, without having to set up a telescope, you just look through a pair of binoculars. You're looking at a lunar eclipse or something like that. So there you have it. And remember, if you're going to do solar astronomy, project it or buy yourself a real solar filter, one that goes over the objective lens. Otherwise, never, ever, ever point the telescope at the sun unless you know what you're doing. With projecting it, and with the solar filter or with a solar filter. In fact, you shouldn't even look at the sun with your naked eye because you can actually damage your eyes. Trust me on that. Okay. Thank you for watching. I hope you enjoyed. I'm going to walk away from the microphone and camera and stop the recording because my computer is way over here. Please subscribe. Thank you again. Stop recording.